Article 430.28 on Exception 1 addresses the requirements for motor taps when the tap conductors are 10 feet or less in length and are not intended for field installation. The core principle here revolves around overcurrent protection. Typically, when tapping conductors from a larger feeder, the tap conductors must be protected against overcurrent. This protection is generally provided by an overcurrent device, such as a circuit breaker or fuses placed at the point where the tap conductors originate. The purpose of this overcurrent protection is to safeguard the tap conductors from overload and short-circuit conditions, preventing potential damage to the wiring and equipment, and mitigating the risk of fire. However, Exception 1 to Article 430.28 provides a specific allowance where overcurrent protection at the tap is not required if certain conditions are met. The first condition is the length of the tap conductors. The tap conductors must be 10 feet or less in length. This limitation on length is critical because shorter conductors are less susceptible to voltage drop and are less likely to accumulate significant heat under overload conditions. The second condition is that the tap is not for a field installation. This requirement suggests that the tap is part of a pre-manufactured assembly or a controlled environment where the wiring and connections are meticulously designed and tested. Field installations, on the other hand, often involve more variability and potential for errors, making overcurrent protection more crucial. Considering a 1000 amp breaker servicing a panel, and a tap is run after this breaker. If the tap conductors meet the two conditions outlined in Exception 1 to Article 430.28, which are being 10 feet or less in length and not intended for field installation, then an overcurrent device on the line side of the tap conductor is not required, regardless of whether the rating or setting exceeds 1000% of the tap conductor ampacity. It is crucial to understand the implications of this exception. While the overcurrent protection at the tap itself is not mandated, the overall electrical system must still provide adequate protection. The upstream overcurrent device, in this case the 1000 amp breaker, must be sized and selected to protect the feeder conductors supplying the panel and the equipment connected to the panel. Furthermore, the tap conductors must have sufficient ampacity to carry the load they are intended to serve. The ampacity of the tap conductors is determined by the load requirements and the applicable tables in the National Electrical Code, such as Table 310.15b16 for conductors in raceway or cable. It is also important to consider any applicable directing factors for ambient temperature, conductor bundling, or other conditions that may affect the conductor's ability to dissipate heat. When applying Article 430.28 and Exception 1, documentation is key. Detailed records should be maintained to demonstrate that the tap conductors meet the length and installation requirements. This documentation may include wiring diagrams, cable schedules, and inspection reports. Additionally, it is essential to ensure that the tap conductors are properly sized for the load they serve. Conducting a thorough load calculation is vital to determine the appropriate conductor size and ampacity. This calculation should take into account the continuous and non-continuous loads connected to the tap, as well as any applicable demand factors. Moreover, proper installation practices must be followed when making tap connections. The connections should be made using approved methods and materials, such as properly rated connectors and terminals. The connections should be clean, tight, and free from corrosion or other defects that could compromise the integrity of the electrical circuit. Regular inspections and maintenance are essential to ensure the ongoing safety and reliability of the electrical system. These inspections should include visual examination of the tap conductors, connections, and overcurrent protection devices. Any signs of damage, overheating, or loose connections should be promptly addressed. Periodic testing of the overcurrent protection devices is also recommended to verify their proper operation. This testing can be performed using specialized test equipment and should be conducted by qualified personnel. In summary, Article 430.28 and Exception 1 provides a specific allowance for motor taps that are 10 feet or less in length and are not intended for field installation. In these cases, overcurrent protection at the tap is not required. However, it is crucial to ensure that the overall electrical system provides adequate protection and that the tap conductors are properly sized and installed. Careful documentation, regular inspections, and proper maintenance are essential to maintain the safety and reliability of the electrical system. It's also essential to consult the latest edition of the National Electrical Code and any applicable local codes and regulations to ensure compliance with all requirements. In addition, it is good practice to consult with a qualified electrical engineer or inspector to address any specific questions or concerns regarding motor tap installations. Here are some additional details regarding conductor ampacity. Conductor ampacity refers to the maximum current, in amps, that a conductor can carry continuously under specific conditions of use without exceeding its temperature rating. The ampacity of a conductor is determined by factors such as the conductor material, size, installation type, and installation environment. The National Electrical Code (NEC) provides tables that list the ampacities of various conductors under different conditions. These tables, such as Table 310.15b16, are essential for selecting the appropriate conductor size for a given electrical circuit. Several factors can affect the ampacity of a conductor. Firstly, the ambient temperature affects ampacity. High ambient temperatures reduce the conductor's ability to dissipate heat, which lowers its ampacity. The NEC provides correction factors to adjust the ampacity of conductors based on the ambient temperature. Secondly, the number of conductors in a raceway or cable affects ampacity. When multiple current-carrying conductors are installed in close proximity, they generate heat that can affect the ampacity of each conductor. The NEC provides adjustment factors to reduce the ampacity of conductors based on the number of current-carrying conductors in a raceway or cable. Thirdly, the conductor insulation type affects ampacity. Different insulation materials have different temperature ratings which affect the conductor's ampacity. The NEC specifies the allowable temperature ratings for various insulation types. Fourthly, the conductor size affects ampacity. Larger conductors have a greater surface area for heat dissipation, which increases their ampacity. The NEC provides tables that list the ampacities of various conductor sizes. To determine the appropriate conductor size for a given electrical circuit, it is necessary to calculate the load current and apply any applicable correction and adjustment factors. The load current is the amount of current that the circuit is expected to carry under normal operating conditions. The NEC requires that conductors be sized to carry not less than 125% of the continuous load, plus 100% of the non-continuous load. Continuous loads are loads that are expected to operate for 3 hours or more at a time. Non-continuous loads are loads that are not expected to operate for 3 hours or more at a time. Once the load current has been calculated, the appropriate conductor size can be selected from the NEC ampacity tables. The selected conductor must have an ampacity that is equal to or greater than the calculated load current. It is also important to consider the voltage drop in the circuit. Voltage drop is the reduction in voltage that occurs along a conductor due to its resistance. Excessive voltage drop can cause equipment to malfunction and can reduce the efficiency of the electrical system. The NEC recommends that voltage drop be limited to no more than 3% for branch circuits and 5% for feeders. To minimize voltage drop, it may be necessary to increase the size of the conductors. Proper conductor sizing is essential for ensuring the safety and reliability of electrical systems. Undersized conductors can overheat and cause fires, while oversized conductors can be more expensive and difficult to install. Therefore, it is important to carefully calculate the load current and apply any applicable correction and adjustment factors when selecting conductors. Here is additional context concerning types of enclosures, such as NEMA 4. NEMA stands for National Electrical Manufacturers Association. NEMA ratings define the types of environments in which an electrical enclosure can be used and provide a degree of protection against specific environmental conditions. NEMA 4 enclosures are designed for both indoor and outdoor use and provide a degree of protection against several environmental hazards. Firstly, NEMA 4 enclosures protect against ingress of solid foreign objects such as dust, dirt, and fibers. This protection ensures that sensitive electrical components inside the enclosure are not contaminated by airborne particles. Secondly, NEMA 4 enclosures protect against ingressive water. This includes protection against splashing water, hose-directed water, and rain. The enclosure is designed to prevent water from entering and damaging the electrical components. Thirdly, NEMA 4 enclosures protect against ice formation on the outside of the enclosure. This is important in cold weather environments where ice buildup can damage the enclosure and impair its functionality. NEMA 4 enclosures are commonly used in a variety of applications where electrical components need to be protected from harsh environments. Some common applications include outdoor control panels, industrial machinery, and food processing equipment. In addition to NEMA 4, there are other NEMA enclosure types that provide different levels of protection. For example, NEMA 1 enclosures are designed for indoor use and provide protection against incidental contact with the enclosed equipment. NEMA 3R enclosures are designed for outdoor use and provide protection against rain, sleet, and snow. NEMA 4X enclosures provide the same level of protection as NEMA 4 enclosures, but they are also corrosion resistant. The choice of NEMA enclosure type depends on the specific environmental conditions in which the enclosure will be used. It is important to select an enclosure that provides adequate protection against all potential hazards. When selecting a NEMA enclosure, it is important to consider the following factors. Firstly, the environmental conditions in which the enclosure will be used. Secondly, the type of equipment that will be housed inside the enclosure. Thirdly, the size of the equipment that will be housed inside the enclosure. Fourthly, any applicable regulatory requirements. NEMA enclosures are tested and certified by independent testing laboratories to ensure that they meet the requirements of the NEMA standards. These certifications provide assurance that the enclosure will provide the specified level of protection. Proper installation and maintenance are essential for ensuring that NEMA enclosures provide the intended level of protection. Enclosures should be installed according to the manufacturer's instructions and should be inspected regularly for any signs of damage or deterioration. Any damaged enclosure should be repaired or replaced immediately. NEMA 4 enclosures offer a robust level of protection against various environmental hazards, making them suitable for a wide range of applications. Understanding the specific requirements of the application and selecting the appropriate NEMA enclosure type is crucial for ensuring the safety and reliability of electrical systems. Let's now elaborate on field vs non-field installations. In the context of electrical installations, the terms field installation and non-field installation refer to the location and manner in which electrical equipment and wiring are installed. A field installation typically refers to an electrical installation that is performed on site, at the location where the equipment will be used. This type of installation often involves running conduit, pulling wire, making connections, and mounting equipment in place. Field installations are typically subject to more variability and potential for errors due to the inherent challenges of working in uncontrolled environments. A non-field installation, on the other hand, typically refers to an electrical installation that is performed in a controlled environment, such as a factory or a workshop. This type of installation often involves pre-assembling and testing electrical equipment and wiring before it is shipped to the job site. Non-field installations are typically subject to less variability and potential for errors due to the controlled environment and the use of standardized procedures. There are several key differences between field installations and non-field installations. Firstly, the environment differs. Field installations are performed in uncontrolled environments, while non-field installations are performed in controlled environments. Secondly, the variability differs. Field installations are subject to more variability and potential for errors, while non-field installations are subject to less variability and potential for errors. Thirdly, the skill level may differ. Field installations often require a higher level of skill and experience, while non-field installations may be performed by less skilled workers. Fourthly, the cost may differ. Field installations can be more expensive due to the labor and materials required to perform the installation on site, while non-field installations can be less expensive due to the efficiencies of working in a controlled environment. The choice between a field installation and a non-field installation depends on several factors, including the complexity of the installation, the time available, the budget, and the skill level of the available workers. For complex installations, a non-field installation may be the preferred option due to the reduced risk of errors and the ability to pre-test the equipment and wiring. For simple installations, a field installation may be more cost-effective. In some cases, a combination of field and non-field installation may be used. For example, the equipment may be pre-assembled in a factory, and then the final connections may be made in the field. When performing a field installation, it is important to follow all applicable codes and standards, such as the National Electrical Code NEC. It is also important to use qualified electricians and to ensure that all work is inspected by a qualified electrical inspector. When performing a non-field installation, it is important to have a quality control program in place to ensure that all equipment and wiring is properly assembled and tested. It is also important to use qualified workers and to ensure that all work is inspected by a qualified inspector. Understanding the differences between field installations and non-field installations is essential for ensuring the safety and reliability of electrical systems. By carefully considering the factors involved in following best practices, it is possible to choose the best installation method for a given situation. In summary, the NEC permits certain exceptions to overcurrent protection requirements for motor tap conductors under specific conditions. Article 430.28 in Exception 1 is key, permitting taps of 10 feet or less without additional overcurrent protection when not intended for field installation. This exception is based on the reduced risk associated with short, pre-engineered taps within controlled environments. The primary overcurrent protection remains the upstream device, sized to protect the entire feeder. However, strict adherence to the length limitation, proper conductor sizing, and documentation of the non-field installation are critical to ensure compliance and safety. Always consult the latest NEC and local codes for definitive guidance and seek professional advice when needed.